No, well, maybe. That's the... Yeah. I guess we should start, right? It's 12:30. It's time to...
Hello? Yes, okay. Okay, let's start this session. Welcome everybody to the session T 2.4, Atmospheric and Subsurface Radionuclide Background and Dispersion. And let's go straight to the first presentation by Anders Ringbaum, Analysis of High Time Resolution Observation of Radioxenon Release from BWRs compared to stack data and reactor operation parameters.
Thank you very much, Romano. Can you hear me? Yes, good. Okay, so this is a presentation on an ongoing work that we are doing at FOI together with people at the Forsmark nuclear power plant in Sweden. We have access to data from the stack measurements for several years, and we have nice measurements in Stockholm, 110 kilometers away from the plant, with two different noble gas systems measuring on the same air. So I will first start by discussing a little bit why do we need to understand radioxenon emissions from nuclear power plants. Then I'll talk a little bit about the Forsmark power plant and show some stack data analysis, followed by analysis of measurements done 110 kilometers away, looking at ratios observed and then also atmospheric transport modeling we have done using an FOI-developed regional dispersion model, and then some conclusions and outlook. So, it's not working. Could I have that? Could you just, if I ask you to change the picture on the desk, on the board? Okay, I go on anyway. Why do we need to study nuclear power plants? Well, as you know, the 95% of the release of radioxenon in the atmosphere is from isotope production facilities. So only 5% of the total release annually is from power plants. So why is it still interesting? Well, first of all, we have sometimes we can have releases from power plants which really are pretty high, up to 10 to 12 becquerel or so. And some of the plants are located close to some of IMS stations, for instance. And even though we expect that the ratios that we observe from power plants will be very different from fresh nuclear tests, we don't always expect fresh nuclear tests. We could also have delayed releases that could be quite similar in ratios to releases from power plants. So we need to know as much as possible about radioxenon emissions from power plants. So this xenon, where does it come from? It comes from contaminated fuel rods. You can have some fuel outside the rods. You can also have some cracks in the fuel cladding, and then you get radioxenon coming out from fission gases. Normally, this is mitigated using delay lines like charcoal bed or sand beds in the plant, which most of the time work very well. But sometimes you can have malfunctions in these, so you get more radioxenon out. And also sometimes in certain operational modes, you have to bypass these delay lines as well. So you can have some releases, for instance, in reactor startup or shutdown. So in Sweden we have 3 power stations, and here you can see them in relation to the sauna systems at the Radionuclide station 63 in Stockholm. And the one we are talking about now is Forsmark, which is 110 kilometers north of FOI in Stockholm. They have 3 reactors, F1, F2, F3. The stack height is 100 meters, and the diameters of the stacks are 3.5 meters, quite big stacks, if you think about it. And the airflow is around 120 cubic meter per second, and the air temperature is around 20 degrees. So that's parameters you use for the atmospheric transport modeling. You do this. This is the exhaust system used in the plant, on all one at each plant. So you start with the air from the turbines coming in here. Then you have a big sand bed, which delays the gas for around 20 hours. Then it goes further away into charcoal columns, which are back flushed like this, back and forth. So you can effectively have hundreds of hours of delay in this stack. And then it goes to a second sand bed, and then here we have a filter for iodine and particulates, and here you have a measurement system, a germanium detector measuring in the stack. So this is the data we have from that. So this is the data you can see from 2016, 1st January until February the 13th, 2019. The 3 different reactors. And you can see here then you have very different, you can have really different releases depending on time and reactor. And you can see there are quite substantial releases here coming out. 10 to 11, almost up to 10 to 12 at late here. And this is 6-hour time resolution on these data points. These releases are due to damaged fuel in reactors, and also due to that the delay lines were not fully functioning all the time. We also have power history from the plant. You can see here for the 3 different plants, and this power decrease is then due to, for instance, routine maintenance, or also some more extraordinary shutdowns because of different actions they were doing. So we can use this power history together with the data and look at what we get. And you can see here, for instance, that reactor 1 has some fuel damage, but here you can see this is the ratio between 135 and 133 detected in the stack. And you can see here that here we have no particular relation with the power history and the data, but here we have. You can see here clearly that the detectable ratios of 135, 133 is really correlated very well with startup shutdowns in the reactor system, which is pretty interesting, I think. The reason it's not here, it's because the delay line was not working so well. So they released all the time. But this reactor is actually have more damaged fuel than this one. This is data from also a 3 isotope plot showing shutdown startup. And you can see here the 3 isotope plot together with the 2 calculated scenarios with the startup and the 35-day shutdown startup cycle. And this is a 9-day startup shutdown cycle. And you can see the data points here. Some of them are where you expect them to be, but there are some outliers here that remains to be explained. I personally believe that this is just large measurement uncertainties. We don't have error bars on these points. But there could be also some other explanations that we have to have under control. We don't know everything what's coming out from these plants. So then I go on to the data set we have measured. Here we have, again, the Forsmark release data all added together to one, all three stacks added together. Here we have data from the Sona 2 and the Sona 3 system in Stockholm. The red bars here are the Sona 2 data, which are 12-hour time resolution. And the black line is Sona 3 data with 6-hour time resolution. You can see the peaks are sharper sometimes, but you also see that the data really agrees very, very well with each other. So they are standing next to each other. And these are analyzed with a new analysis method, which is described in a poster. Here are observed ratios. Green ones are Sona 2, blue ones are Sona 3. And you can see that we have a lot more blue points than green ones. And that's because we have a much more sensitive system. We have twice as many samples per day as compared to Sona 2. The sensitivity is increased as well. You can see they fit pretty well with what you would expect from the scenarios calculated, but there are some outliers also here. And here we have the 4-isotope plot. And this is actually the first time we can observe all 4 isotopes at the same time at many samples. We haven't been able to do this with the Sona 2 systems. But here we have like 20 data points during this time period with all 4 isotopes, and which gives us much more knowledge, I would say, about what's going on. This is the individual ratios plotted as well. Also here we have some higher ratios for the metastable ratios, but the 135 ones are pretty what you would expect according to scenarios. It's not working again. Could you please switch for me? Press the button. Thank you. Page down. Yeah, okay. So we have some high 131M detections also, and these are not coming from the reactor. They are coming from somewhere in Central Europe, where we have located that with atmospheric transport modeling. Next, please. Can't you just use the board? It's not working. It's not the keyboard. Can I just press the button on the keyboard? Okay. Okay. The final part of my talk is about atmospheric transport modeling. At least we have a model at FOI which is used by the Swedish Radiation Protection Authorities called PELO. It's also used by the Swedish Armed Forces and it's developed at FOI. It's a regional model, Lagrangian dispersion model, and there are a few publications out on that one. If you come up to me, I can give you those references later. The resolution is on the weather is 0.1 degrees. And we have calculated in 6-hour time resolution bins the weather. And also remember that the data from the stack release is also 6-hour time release. So we use the data from the stack together with this model and try to predict the plumes observed in Stockholm. And I hopefully soon will be able to show you the result we got very quickly. Next. So I skipped that one and that's just the description of the model. Okay. Like I said, we simulated quite a large time period, and here you have the results. This is in the second half of 2017. The red ones are the predicted plumes, and the black lines are data from Sona 3. And you can see here we have a few plumes predicted, and they are also observed in the data. And I think also both in time and also in absolute concentration, it looks very good. Here are January to June 2018. There are a few plumes predicted, but also we have a lot of other things, other sources coming to the station. So it's not so easy just to say that this plume is from Forsmark, because there are also other sources mixed up with this. And you can see this here. Here are some more plumes predicted. We have more releases in this period, but what's important here is that all predicted red plumes are actually also observed at the station. So I think it works really well. But there are maybe factor 2, 3, or 4 off sometimes. Sometimes they are spot on. But that's what you could expect, I think. Here one other example. We also compared with high split, another model, and you can see that we have a qualitative agreement between these two models. But there are some differences. And it should be, because the resolution of the high split is not as good. So this is a summary. This is the most extensive data set observed, set of observed releases from a nuclear power plant reported to date. We have analyzed this together with stack measurements. We see reasonable agreement with models and isotopic ratios, but we see some higher metastable ratios. We see correlation between stack data and startup shutdown. And we need to be able to model the reactors a little bit better. We have a regional model at FY that agree well with observed peaks. And I think this also shows the power of the new generation noble gas systems. It gives us much more data and much more precise data. And the last point is crucial to have a good communication with the nuclear power plants to get insight into these detections. Thank you.
Thank you, Anders, very much for this very interesting presentation. Unfortunately, we saw a lot of science and not so much technology. Let's see if we can improve that. The next. Any question to Anders? Ted?
Could you put your three isotope plot up?
Maybe. This one? Or?
Yes. So my question is, have you thought about the fact that the data for the three isotope plot falls to the wrong side of the correlation plot?
This one, here.
Yeah, because of, well, have you thought about why that might be?
I think that's one of the crucial questions here. It could be actually that we are a little bit wrong in the theory, I don't know, in the model itself. Because I see this all the time, that the ratios are a little bit on the high side for the metastables, 133M. And I've looked into the calibration of the data. Is it a calibration issue with the systems? It's not. I really stress tested the calibration. I can't find a problem there. So remains to be investigated, I think.
Any more questions? Okay, thank you again.
Hello again.
So we have only one microphone working?
Okay, so now I'm here, at this position instead. So now we have a second presentation, which is Carlos Eduardo Bonfim going to talk about application of computational fluid dynamic in the atmospheric dispersion of radionuclides at Fukushima disaster. Please. Okay.
Hello everyone, good afternoon. My name is Carlos Eduardo. I'm a chemical engineer in Brazilian R. Okay. Initially, I'm going to make it to a brief presentation about a military organization for which I work. Okay, and we can be seen in this picture here. Located at Rio de Janeiro, Brazil, the Chemical, Biological, Radiological, and Nuclear Defense Institute is a part of the Brazilian Technology Army Center, and together comprise all this building area here and the green area here. Okay. On the objective, the institute is research and development of defense products in area of CBRN defense. For this reason, it has 11 labs distributed in 3 defense sections: chemical defense with 4 labs, biological defense 1 lab, and radiological and nuclear defense 6 labs. This work, it will be presented, is being developed at the Institute as a benchmark for emergency activities in Brasilia plant, located in Angra dos Reis, Rio de Janeiro. After the tsunami in accident in March 2011 at Fukushima plant, released 10 by the 15 radionuclides of the air after a meltdown and explosion of the reactors. CFD was chosen to predict the concentration, airflow, and dose and other parameters, and it consists in continual flow to close the real situation. And here we have the step-by-step CFD, the model. Okay? The geometry was based in Unit 1, Fukushima plant, and was made in 2D models instead of 3D models to lessen the computational effort. For instance, the 3D model, it has 57 times more elements than 2D models. We have seen 7 million elements, and 2D models we have 124,000 elements. Okay. Here we have physical definition of the problem, okay, and the validation of the experiment was done using the experiment Brusca. As expected, the presence of obstacles near the launch point causes a disturbance in the airflow, generation, recirculation zone, and little vortex we can be see here, and according to literature, which directly influence the concentration and level dose here. And for conclusion, the use of CFD for the calculation of the atmospheric dispersion allows a more realistic simulation of the lens conditions and feature a greater accuracy the Gaussian model. And we here a brief comparison between the models, CFD with obstacles and Gaussian plumb without obstacles. So the future implementation of this work is use of the turbulence models. In this job, we use K-epsilon turbulence model, evaluation of the atmospheric dispersion, study of radionuclide transport in surface waters, and study of 3D model using supercomputer. In Brazil, we have the Santos Dumont computer, and application in Angra dos Reis plant. Okay. This the reference to this work, and thank you for our attention.
Thank you very much. Do we have any questions from the audience? Yes?
Thank you for the presentation. My question is, how much CPU timing used to do the...
Sorry?
How much time take from you to do the computational for this one? Because the mesh, it should be small mesh.
To the models?
Yeah, how much time? CPU time. CFD take time to
Okay.
for huge geometry.
Okay, thanks. And so, one week, we have 1 week, because the 3D models, one week, and 2D models, 1 day.
Running.
1 day. 2D models.
Do you use the energy equation with it?
Yes.
You solve all Navier-Stokes equations inside? And
Navier-Stokes equation.
how big the mesh for the mesh?
The relation time, 10 by 4 power.
Thank you.
Any other questions? Okay. Then, thanks again.
Thank you.
So now our next presenter is Paolo Tristan. I would like to invite him to the podium. He will present assessment of temporal variations of natural radionuclides, beryllium-7 and lead-212 in surface air in Tanay, Philippines.
Good afternoon, everyone. So I'm Paulo Cruz. I work at the Philippine Nuclear Research Institute in Manila, Philippines. And I'm here to talk about our assessment on the temporal variations of natural radionuclides in Tanay, Philippines, where our IMS radionuclide monitoring station is located. So aside from being used to determine natural background radioactivity, we can actually use natural radionuclides such as beryllium-7 and lead-212 as tracers for environmental processes. And the understanding of the behavior of radionuclides in aerosols and atmospheric processes that affect radionuclide distribution around the world is actually beneficial for the effective implementation of a nuclear and radiological emergency preparedness and response system. However, based on what we know, the studies on the temporal variations of natural radionuclides in surface air, particularly in the tropics between the 0 to 25-degree band from the equator, have been scarce in previous literatures. Most of the studies on natural radionuclides in surface air are in areas above this tropical band. In particular, in Southeast Asia, the studies on the spatial and temporal variations of natural radionuclides in surface air are quite limited. Of course, there are studies on depositional fluxes of these radionuclides. However, those are constrained within short study durations and usually rely on rainfall data. So. Also in the Philippines, we haven't really done any research on this, and this is the first study that we did on this topic. So we took advantage of the detection capabilities of the radionuclide network of CTBTO's IMS International Monitoring System, particularly the data coming from our radionuclide monitoring system RN52 or PHP52, located in Tanay, Philippines. So the purpose of the study was to determine the seasonal variations of beryllium-7 and lead-212 in surface air, to identify the atmospheric conditions and processes affecting radionuclide concentrations in surface air, to understand the atmospheric dynamics involved in the global distribution of radionuclides in the atmosphere, and of course to be able to utilize the CTBT's IMS data and IDC products for various civil and scientific applications. So for us, we're quite familiar with the methodology. So we have 24-hour sample collection, followed by a 24-hour decay process to remove short-lived radionuclides, followed by a 24-hour analysis by gamma spectroscopy, and these are all automatically sent by our stations to the IDC, which NDCs can then further retrieve using various methodologies such as the NMS client, the AutoDRM, and the web-based CR tool. For the results, so we find here that the concentrations of beryllium-7 and lead-212, monthly concentrations in 1 year. So our beryllium-7 concentrations in surface air range from about 7 nanobecquerels per cubic meter to as much as 11.2 millibecquerels per cubic meter. And as you can see here, high concentrations of beryllium-7 are observed between the months of January to April, followed by a decrease in concentration during the rainy monsoon season between May to September, and then an increase again between the months of October to November. This actually, interestingly, this actually coincides with the prevailing monsoon winds in the region, wherein the southwest monsoon are prevalent between the months of May to September, and then the northeast monsoon being prevalent between the months of October to March. So quite a coincidence. For lead 212, on the other hand, we see a different trend, in a sense that we see high concentrations occurring between April to June, which actually coincides with the warm, dry summer season in the Philippines. And concentrations range from 1.3 to 106 millibecquerels per cubic meter. We tried to correlate the activity concentrations of our beryllium-7 and lead-212 to determine the correlation between each other. And based on this graph, we see that there is no correlation between the two, which suggests actually that that atmospheric processes occurring within the Philippines affect both radionuclides independently. We also did a correlation between beryllium-7 and lead-212 concentrations with atmospheric parameters such as ambient temperature, relative humidity, and total precipitation in millimeters. Out of all the correlations, we found that only lead-212 and temperature have a strong positive correlation, whereas all other correlations are negative, have a negative correlation, albeit in different degrees. Interestingly, also, as compared to other literature wherein it's reported that precipitation is the major factor in the removal of radionuclides in surface air, we find that actually relative humidity shows a higher degree of relationship between radionuclide concentrations in surface air. And we think that being a warm, humid, tropical climate, tropical country such as the Philippines, the high humidity in the region or in the area actually contributes more in the removal of radionuclides in surface air. And one reason that we think is to be so is because increase in relative humidity would mean more water molecules present in the air, which means there are more sites for nucleation, which then leads to further removal of your radionuclides in surface air. So this table just further summarizes our data. So as you can see here, you have higher Pearson's coefficient values between radionuclide concentrations and relative humidity as compared to your precipitation. And lead-212 is the only one that presents a strong positive correlation with your temperature. And this is actually agrees with literature, with scientific literature, wherein lead-212 is greatly affected by ambient temperature. Now, to further explain, so the results of our study actually shows similarities with that observed on depositional fluxes in Shanghai, China, wherein you see high beryllium-7 concentrations during the months of January to April, during late winter to spring, and followed by a decrease during the summer, and followed by another increase in beryllium-7 concentration during the fall. And this has been associated with the large-scale subsidence of beryllium-7 rich winds from the stratosphere and upper troposphere, where it is continuously being produced, as compared to the lower troposphere. So you really have to have an introduction of your beryllium-7 rich winds for us to have higher concentrations in surface air in the ground. For lead 212, as mentioned earlier, well, surface air concentrations are dependent on the emanation rate of their parent noble gas, and for lead 212, this would mean the emanation rate of your thoron gas, which is affected by various parameters such as soil moisture content, temperature, wind speed, air pressure, and so on. And the higher temperatures experienced during the months of March to May result to warmer and drier soils, thereby increasing the thoron release into the surface air. So for the conclusions, we find that the atmospheric conditions and processes affect surface air beryllium-7 and lead-212 concentrations in Tanay, Philippines independently. Surface air lead-212 in Tanay increase with warmer ambient temperatures, and strong stratosphere-troposphere exchange of air masses increase surface air beryllium-7 concentrations in Tanay, Philippines. So these are our references. And this study might not have been possible if it weren't for the help of CTBT for providing us the technical support as well as our capacity building by providing us with the training on the access and analysis of IMS data and IDC products held here in VIC in Vienna in 2016. And actually, I'm very proud to say that this has resulted to my first international publication, and I encourage everyone here to access our research paper through this link. It's available for download until August 3 of this year. So you're all welcome to access our papers through that link. So again, thank you very much, and this ends my presentation.
Thank you very much. I have just a question.
Yes.
You show anti-correlation with humidity, with concentration, I guess, on both on lead and
Yep.
the one before you.
Yep.
Yes. So I was wondering, have you checked if the filter height is always the same during this?
Sorry.
Could this be that there is water in the filter? The
Well,
filter efficiency is then underestimated.
Well, that is also one thing that we were, I guess one factor that we were not able to consider because in our station we are not able to measure water content in the filters.
To me, I think it's just the filter height.
Yeah,
If
so
you cannot press it as it should,
yes.
then you are underestimating your
Yes,
concentration.
on this, based on, of course, on the pressing of the air filters are standard. However, this data that we received are all retrieved from the CR tool. So, yes, there might be some, like as you mentioned, water on the air filters that might have also affected the data, but. Yeah, that is possible. So unfortunately, we were not able to verify that with actual monitoring.
We may access to this data from the station operator if you're interested.
I am the station operator and also the
Okay.
NDC analyst, so I have all the.
So you didn't log it on every day on this?
Unfortunately, based on our procedure, we do not have a measure for moisture content in the air filters. So when we press the filters into a disc, we don't normally measure the water content as part of our routine
But
monitoring.
are you measuring the height of the filter?
As well, no.
No.
We
Okay, no problem.
only do the standard
Okay.
containers. So, but yeah, I guess in practice, that's a good suggestion. I will consult it with my colleagues, and maybe we could do something about it as well to better improve our data.
Thank you.
All right.
Any more questions? Please. Yeah, but this is after pressing.
Yes, because normally when you do the processing, you still press the paper, you still press the filter into a small disc, and yes, sometimes especially during very rainy during rainy days, you have filters that have very much water contained in it. So yeah, sometimes it could also affect the height, the pressing of your filters. So.
In fact, we have a station which has a lot of humidity, and the station operator is leaving for 24 hours, unpress the filter, and then he press after the 24 hours. So this could be a possibility.
Yeah.
But first, it would be nice to understand if there is
Yeah.
any relation with this.
Yeah, the 24 hours is only for the decay to remove the short-lived radionuclides, which could affect, interfere with your gamma peaks. But again, even if lead-212 and beryllium-7 has short half-lives, they're still strong enough in concentration. After collection, yes. No. You after 24-hour collection, you press the filter into a small 5 millimeter disc, and then yeah, your stations are provided with a sample container.
Ted?
Thank you for your presentation. It's very interesting.
Thank you very much.
I have to say that I've never seen a correlation with temperature for a radon daughter in that way, so that was quite interesting.
Thank you very
to
much.
note. Did you either look at a correlation between larger land masses that may be providing the air to the Philippine station or the ambient pressure? There should be a correlation in pressure. That's a sort of well-known fact.
Thank you very much for that question. Unfortunately, for this study, we were not able to look into atmospheric pressure that much. One of the main reasons is that during within the study duration, we were having problems with our meteorological sensors. In pressure, atmospheric pressure is not that reliable, I guess. So we decided to focus only on these three atmospheric parameters. But that's a good suggestion. We will look into that as well. With regards to other radon daughters coming from other areas that might contribute to the concentrations that we find here. Of course, there are studies that use lead-210, which is actually a daughter radionuclide of your radon, which has a longer half-life as compared to lead-212. Unfortunately, given the amount of data, we were not able to analyze that much, because unlike beryllium-7 and lead-212, these two radionuclides are automatically reported by the IDC regularly. So if we were to analyze radon daughters, we would have to analyze each and every spectrum individually. So given the amount of data that we have to analyze for this study, it would be quite difficult. So maybe in the future, when we do our one-year analysis, then maybe we will have enough time to review lead-212 in comparison with lead-210 and see what are the possible contributors to radionuclide concentrations in surface air.
Okay, thank you very much. I think we should go on to the next speaker. So thank you again.
Thank you very much.
Yes. So we now have a contribution from Punua Taebi. Contribution of all nuclear research reactors to the global radioxenon emission inventory. Please.
Thank you. Hello and good afternoon, everyone. This presentation is a part of a study during an internship at CTVTO. The aim of this study is answer to this question, whether the nuclear research reactors, whether the source strength of nuclear research reactor is below the level that may have an impact on CTVTO IMS observation. You know that radioxenon provide a signature of an underground nuclear explosion. These isotopes are frequently detected by IMS noble gas systems, and these radioxenon can also be released from different nuclear facilities, such as nuclear power plants, medical isotope production facilities, and nuclear research reactors. The contribution of nuclear power plants and medical isotope facilities to radioxenon emission are very well known. These are the annual release of these facilities in becquerel per year. The medical isotope facilities are the main source of radioxenon in the atmosphere. Nuclear research reactors are the only source of which the xenon releases haven't been systematically assessed yet. Nuclear research reactors have different varieties than nuclear power plants. This can be demonstrated by different thermal power from the smallest to the largest one. In this table, you can see the different category of nuclear research reactors according to their thermal power that were worked in different times. Whereas the releases from nuclear power plants is very well known, there are a few publications on nuclear research reactors, and this table summarizes the releases data based on measurement for 8 nuclear research reactors. The data presented here for HFIR and RA3 are the median of 10-year emission. Nuclear research reactors have much larger, different operational schedules from a few hours to several days. And by knowing the working hours of the nuclear research reactors, we can calculate the capacity factor, that is a fraction of time that the power is on during a year. Some research reactors, like Opal, work in a continuous mode, so the capacity factor here is 100%. But the most reactors work in non-continuous mode, so the capacity factor for them is below the 100% for the reactors that for which no available data are for their working hours. We use the median of the available data, which is 13.20. And there are two different sources of radioxenon emission from nuclear research reactors, which are fission and activation. For most reactors, one of these two procedures is the dominating source of emission, and both contributions should be considered as a total emission from nuclear research reactors. Now here is the procedure to find the contribution of fission to the radioxenon production. At first, we need to know how much radioxenon is released from nuclear research reactor, and this can be calculated from this equation, in which B is the fission birth rate, lambda is decay constant, Y is cumulative fission yield, C is capacity factor, P is thermal power, F is typical fission energy, which is 200 megaelectronvolts. This is a factor that converts megaelectronvolt to megajoule, and this is number of seconds per year. Because of lack of data on releases from nuclear research reactors, we need a best estimate to made from extrapolation which are founded in empirical data and theoretical understanding. In this figure, you can see the release to birth ratio for different noble gas isotopes as a function of lambda, and this is for an MPP. This figure known as a boost plot, and it has the advantage of providing the release to birth ratio without need to know how the xenon release from where it generates to and emits from different compartments of the reactors. We have a fitting line here that is described with this equation, which is the Booth equation, in which R is release rate in becquerel per year, B is birth rate that we calculated from the previous slide, K is a constant, lambda is decay constant, and alpha is an exponential parameter. These blue signs are for old MPP, which was measured in 1969, and it has a slope of 0.636. And these red signs are for a new nuclear power plant, and this shows that this equation is still valid for new nuclear power plants, and the steeper slope shows that new power plants have longer retention time. So we apply the Booth equation for estimate the release from nuclear research reactors. In this plot, you see all the nuclear research reactors that have an important role in this study. To determine the parameter alpha, we use the data from FRM2, Hannaro, and Vienna reactor. And to determine the parameter K, we calculate from the xenon 133 releases from these 6 reactors, and the Booth equation for nuclear research reactors calculated from this equation. And now here is the contribution of activation to radioxenon production. For this calculation, we have two reactors based on their measured data. The Trigo reactor from Texas University. For this reactor, there are 2 pathways for release of xenon, which are argon purge stack and HVAC stack. We know the flow rate of air from this stack, and we have the measured data on activity concentration of xenon 133, so we can calculate the release rate of xenon 133 from this stack, and we have the same calculation for HVAC stack. So by adding the result of these 2, we have the total release from this reactor. By considering the capacity factor and the power of these reactors, we can have the scaling factor of xenon 133 from this reactor in becquerel per kilowatt hour. For HFIR reactor, we have a 10-year median release rate of xenon 133. Here also, by considering capacity factor and the power, we have the scaling factor for this reactor, and the average of these 2 values make for us the scaling factor for xenon 133. For the other isotopes of the xenon, we use the activity ratio from air activation, and by considering the scaling factor of xenon 133, we can obtain for the other isotopes the scaling factor. So the release rate can be calculated for activation based on this equation, which is capacity factor multiplied by a scaling factor and the power of the reactor, and the numbers that converts year to hour per year. So the results, here you can see the annual releases of nuclear research reactors based on fission and activation. You can see for all isotopes, the contribution of activation is more than fission. Here in this plot, we have box and whisker plot for fission on the right and activation on the left, and here is also presented that the contribution of activation is much more higher than fission. And in 4 isotope pellets, we have 2 parts that are separated by this red line, which is discrimination line. On the right side, we have the nuclear explosion events. On the left, we have the civil activities. These three green signs shows the isotopic ratio for Hannaro, Vienna, and FRM2 reactors. This is the isotopic ratio from our calculation, which is based on boost pellet, and these are from fission-based releases. Here, this plus signs shows the 10-year measurement of xenon releases from HFIR. This star shows the median of this 10-year measurement, and here is the isotopic ratios based on our calculation. And you see that the 4-isotope plus shows a clear distinction between fission sources and activation sources. Here is the comparison between the nuclear power plant and nuclear research reactors. Here is the European reactors, and it is the release rate of xenon 1 through 3. And this line shows the total release for the research reactors in 2014, which are 160 research reactors. And here you can see that this total is smaller of some individual nuclear power plants. And the conclusion in this study, the contribution of all nuclear research reactors in global emission of radioxenon is measured according to the few available experimental data and using the boost pellet based on fission. The activation contribution in radioxenon releases is also estimated. If activation is dominated in xenon 1 through 3 releases from the nuclear research reactors, it seems to be an order of magnitude higher than the fission releases. The difference is even stronger for the other isotopes. According to this estimate, the world's entire research reactor fleet releases xenon 1 through 3 in the order of magnitude of 5 gigabecquerel per day, which is reasonable radioxenon releases. In 2014, the total releases of 160 nuclear research reactors together is still less than the release of many individual nuclear power plants. And the distribution of source strengths for nuclear research reactors and nuclear power plants are overlapping. There are 4 nuclear research reactors in case of fission dominating, or 20 nuclear research reactors if activation dominates, with a daily release more than 0.1 gigabecquerel per day. These are a stronger source than the 41 weakest emitters among nuclear power plants. Therefore, nuclear research reactors cannot be ignored as the source. And these are the references. Thank you for your attention.
Thank you very much. So, questions, comments? Okay, I have just one just comment. I think, well, this is then the last main source to be really investigated. I think it's nice that it has been done.
Okay.
So on. Yes, Ted.
Thank you for the presentation.
Thank you.
It seems counterintuitive to me that activation could be greater than fission in the releases for most of the traditional release mechanisms. The only thing I could conceive of is if the fuel rods in research reactors are tighter or better, the xenon's better contained in the fuel for power plants, or for research reactors than power plants. But what is your explanation about why activation could be a greater release than fission?
We have some evidence from Texas reactor. They haven't seen any releases from fission based, and activation is mainly from the activation of air dissolved in water pool. Yeah.
I guess following on from that question, do your figures include experiments where they've been irradiating fuel but then processing it? So is it just the releases from the operation of the reactor, or is it releases from hot cells where they've been...
No, just reactors.
Okay, so
Yeah, just
not the
nuclear.
experiments associated
No,
with reactors.
no. Because these are because the hot cells are for medical isotope production facilities, and we just consider the nuclear research reactors.
Okay.
Okay, I just want to add one small comment. I think it's important also here to remember that anything can happen. I mean, when you have, this is a kind of a generic release factor that you get from this, but then you can of course have damaged fuel and so on that can really increase these numbers a lot. So we still have to really keep track on also these kind of reactors. Yeah. Okay. All right. You want to? I do that? Okay. Okay. So thank you very much.
Thank you.
So now it's time for Andreas Bollhofer from Freiburg, who will talk about half a century of krypton-85 measurements in the atmosphere of Central Europe. Please.
Thank you, Anders, for your introduction. I'll present some krypton-85 activity concentration data measured over the approximately past 50 years in Central Europe and also in the Southern Hemisphere. And this is a collaborative study between mostly the BFS, but also partners in Switzerland at Heidelberg University and CSIRO in Adelaide, Australia. I'll give a short introduction about sources and uses of atmospheric krypton-85. I'll talk about sampling and measurement procedures at the BFS lab in Freiburg. As I said, I'll present some results of krypton-85 in Central Europe and the Southern Hemisphere, and provide an outlook on data availability in my conclusions. This is just a bit of a history of the nuclear age, I suppose. It all started with the Manhattan Project in August 1939. The first reactor went critical, that was Chicago Pile number 1 in 1942. And in 1944, the potential of sniffing for radioactive noble gases was already realized, and US Air Force airplanes looked for evidence of nuclear weapons or nuclear reactors programs in the air above Germany. The first nuclear weapon tests were followed by the devastating nuclear bombs in Hiroshima and Nagasaki, and in the late 1940s, the global krypton-85 monitoring program instigated by the US and British intelligence started. From the early 1960s, Germany started to measure krypton-85 and also xenon-133 in the atmosphere in Germany, and since 1972, those measurements have been continuous. The krypton-85 sources, the main source is nuclear reprocessing, with about 20 terabecquerels of krypton-85 emitted per kilogram weapon-grade plutonium produced. It can thus be used for the verification of reprocessing activities, so that means for verification of plutonium production. For the verification of the non-proliferation treaty, it's very useful as an environmental tracer due to its relatively long half-life of approximately 11 years. So it's used for atmospheric transport model studies and also for groundwater studies, and I'll talk about that a little bit later. Presently, krypton-85 is in the atmosphere at becquerels per cubic meters levels. This shows a plot of the active reprocessing plants in globally. You can see the red dots here. They are the active reprocessing plants, and they are all located in the Northern Hemisphere. There's a couple of decommissioned reprocessing plants in the Southern Hemisphere, and this makes krypton-85 in particular useful for the study of interhemispheric exchange between the Northern and the Southern Hemispheres. These are the sampling sites of the BFS, the Bundesamt für Strahlenschutz in Germany. We've got 3 sampling sites in northern Germany, in Hamburg, Brunswick, and Berlin and Potsdam. Central Germany, we've got two sampling sites in Trier and Perl, and also in Offenbach. In southern Germany, we've got a sampling site in Freiburg, and also on top of Mount Schauinsland, about 1,200 meters above sea levels, only 15 kilometers apart from Freiburg. And we also sampled for krypton at the Jungfraujoch in Switzerland at 3,545 meters above sea levels. We've got the two major, or the two reprocessing plants here, La Hague in France and Sellafield in England. And this is an old reprocessing, a pilot reprocessing plant in Karlsruhe that operated from 1973 to 1990. Karlsruhe is located in the Rhine Valley, as is Freiburg, and that has had an impact on the measurements of krypton-85 in Freiburg, as you will see in a later slide. In total, we have thus far analyzed more than 12,000 individual krypton-85 samples from our network. This shows the annual releases of krypton-85 from La Hague and Sellafield, and the gray line indicates the ratio of the Sellafield emissions to the La Hague emissions, and you can see up until about 2004, the ratio between Sellafield and La Hague is approximately 0.5, and from 2005 onwards, the emissions from Sellafield dropped, and the ratio is only about 0.2 to 0.25 from 2005 onwards. The sampling for krypton we conduct with a manual system that was developed in 1973, and it was developed for the measurement of atmospheric activity concentration of both krypton-85 and xenon-133. As I mentioned, we've got a worldwide network and a central lab in Freiburg. The sampling is done cryogenically. The air is basically driven over liquid nitrogen-cooled activated charcoal adsorber. And after sampling, the noble gases are processed and purified using gas chromatography. The activity concentration of krypton-85 is then measured in 8 proportional gas counters, which are lead shielded and have anti-coincidence counters installed as well. The minimum detectable activity for krypton-85 is typically 30 millibecquerels for 1 cubic meter air sample. Now to the results. That's the results for our southerly sampling sites, Freiburg, Schauinsland, and Jungfraujoch in the Swiss Alps. The Freiburg timeline is a red line here. Green is the Schauinsland, and black is the Jungfraujoch. Jungfraujoch sampling started in early 1990s. One thing that you can see is that if you plot the Schauinsland data, that's the data from the Mount Schauinsland, 1,200 meters above sea level, against the data from the activity concentration measured in Freiburg, that from 1970 to about 1990, the concentrations in Freiburg were significantly higher, in particular in wintertime. The gray line, or the gray bar plot here, basically that shows the annual emissions of the Wiederaufbereitungsanlage in Karlsruhe. That's a pilot reprocessing plant in the Rhine Valley. And frequently forming inversions in the Rhine Valley inhibit an effective exchange between bottom air and air at higher altitudes, and that's reflected in the higher activity concentrations measured in Freiburg as compared to the Schauinsland. From 1990 onwards, in 1990 the reprocessing at the pilot reprocessing plant in Karlsruhe stopped. You can see that there's virtually no difference between activity concentration measured at those two sites, Freiburg and Schauinsland. Down here you see the monthly emissions in petabecquerels per month from La Hague. You can see a typical kind of an annual variability with almost no emissions during summer, and they coincide with very low or reasonably low activity concentrations measured during those times, and these summer periods are those when there is vacation time in France usually. From the data that we have, we calculated a baseline, which is the black line here, and also an average. And that baseline for the Krypton 85 activity concentration was calculated by taking the quarterly minima from all Central European stations and then fitting a 7th order polynomial fit to the quarterly minima. And that's the black line here. We can see that there is a sort of a steady state, or maybe even a bit of a decrease in the baseline between 2009 and 2014. And the levels during that time were about 1.39 becquerels per cubic meter, so that's the baseline levels. And from that, assuming that it's a steady state, that means as much Krypton 85 is released into the atmosphere than what decays, what's present in the atmosphere. We can calculate that about 3.2 by 10 to the 5 terabecquerels per year were released during that time period into the atmosphere, which is equal, or which equates to about 10 to 30 tons plutonium production per year, depending whether it's weapons grade or reactor grade plutonium. The total atmospheric krypton inventory during that time was about 5,100 petabecquerels. We've also calculated an average. Basically, we used the average from all our stations and calculated the quarterly average and then fitted a 7th order polynomial fit to that. And we did that to provide input functions for dating of young groundwaters. So the idea here is that the Krypton 85 to Krypton specific activity is the same in the air as is in water droplets, and then the water that's incorporated into the groundwater body has the same Krypton 85 Krypton activity, specific activity as well. And if we assume a simple piston flow model, that basically means that what comes in from the top is then produced along the groundwater body without any losses, we can determine ages of groundwater sampled at particular wells. So for example, if we have a 1 becquerel per cubic meter Krypton 85 concentration in a sample collected in the 1st of January 2018, we can do a decay, backward decay model and calculate that this sample, if we assume that it's been incorporated into the groundwater body at baseline concentrations, was incorporated in about 2013. If we think it might have been incorporated at higher concentrations or closer to active reprocessing, it would have been incorporated in about 2010. We can, with this, calculate the average age difference between, or the age difference between using an average input as an input function or the baseline, and that for concentrations between 0.4 to about 1.3, 1.4 becquerels per cubic meter. The age difference between the two is not that big really. It's about 3 years using either the average or the baseline input function. These data have just recently been published, and I'm happy to provide the link to download this paper as well. Just quickly to the results for the other station in Central Europe, and I'm just going to present the very general findings. So we have a high correlation between the northerly sites, the central sites, and of course Freiburg and Schauinsland as well. And the correlation between the sites is lower for these various areas. However, one thing we found is that from about 2005 onwards, that the correlation between the sites increased, in particular in those areas here, and we believe that might be an effect of the dominating influence of a single source, so the dominating influence of Le Hague. Now quickly to the results from the southern hemisphere, and that's I'm trying to summarize our results from a paper that is currently in preparation. We have activity concentration that are being measured currently in Adelaide. These are data from Darwin here. There's a gap in the Southern Hemisphere data here. And these data were sampled at the campus at CSIRO in Adelaide. Using these data, we can estimate an interhemispheric exchange time. And by doing that, we basically use the we model the Southern Hemisphere baseline by taking the Northern Hemisphere baseline and taking into account the exchange time between the Northern and the Southern Hemisphere. By extrapolating the Northern Hemispheric baseline and minimizing the psi squared of the extrapolated Northern Hemisphere baseline to the Southern Hemisphere data that we have, assuming that basically the profile that we measure in the Southern Hemisphere is smooth and the peaks that we frequently see in the Northern Hemisphere are not visible in the Southern Hemisphere anymore. So by minimizing this psi squared, we can determine an exchange time tau of about 1.2 years between the Northern and the Southern Hemispheres. We can also see an annual variability, which is sort of quite high in 15-16 and 16-17 and 17-18, but lower in the preceding and the years after those particular years. And we believe that this annual variability may have to do with the movement of the Hadley cell, and that the strength of that variability is influenced by the ENSO cycle. Now, to my last slide, a bit of an outlook and conclusions on data sharing. So the data from Freiburg, Schauinsland, and Jungfraujoch are publicly available under that link. And these data will, of course, be useful in particular for dating young groundwaters. The Central European data will be available soon on the BFS geoportal. That's a geoportal that we currently use to make public the measurements of the German dose rate network, for example, or the particulate monitoring networks. We also want to put the Krypton 85 data on there, and also the Xenon 133 data that we measure, and update it regularly so that researchers elsewhere can use the data as well. The development of atomic trap trace analysis means that there is more precision in the measurement of Krypton 85 with lower sample sizes, and that will help to continue the time series and also the geographical spread of analysis worldwide, and allow for additional groundwater applications. And despite the predictability of the Southern Hemisphere baseline, monitoring is of course still required for verification purposes. Thank you.
Thank you very much, Andreas, for your nice talk. So, questions? So these data what's the time resolution? Remind me again. It's like how many days?
The sampling period is usually seven
days. Yeah, okay.
But we do take samples on a daily basis as well in big aluminum bags. So if we do have a particular week with particular high concentrations, we then have daily samples as well.
But it means that the variations in peaks you see, that's more weather related than operational peaks from releases.
It's a bit of both. So usually the main, I forgot to explain that the main wind direction basically blows from La Hague towards central and northern Germany. So if there's a release, we can see the release in our weekly samples. But because we only have weekly samples, the daily analysis of daily samples give us more information on where exactly the source is. And usually, when we do the backward ATM, it shows us that the releases are from La Hague. And if there is, as I said, during summer vacation, usually the levels are background or baseline levels that we measure throughout Germany.
Okay. You also mentioned that you had correlation increasing when you have only one source. Could you just explain a little bit how that works? How you get high correlation because of that?
The idea there is that the northerly, if we look at ATM, the northerly sites in Germany would be more influenced by emissions from Sellafield than at La Hague. So if you have two sources, so basically contributing at different strengths at the particular sites, you would expect worse correlation than if you have only one source influencing the activity concentration that you measure. So we believe that this increase, we still have to delve deeper into the analysis of the data than just having a first look at it, but we believe that the decrease of the emissions from Sellafield might have to do with the fact that the correlation between the sites actually increases. And we do want to basically resolve it on an annual basis as well to see whether the correlation indices actually correlate with the annual emissions from the two sites as well.
Okay, thank you. Okay, so then thank you again. Nice talk. So now we go on to the next speaker. Judah is there, yes. Judah Friese from PNL. He will talk about high-resolution stack data from fission-based molybdenite production. Please. And I just also remind you that the next talk is cancelled, so we have one more talk after that.
All right. Good afternoon, everybody. I want to, first of all, start thank with my collaborators on this project. I have the delight of working with some folks at IRE as well as ANSTO, which are the two facilities we're going to be talking about today, and some of the high-resolution stack data that we have from them. And well, let me just go to the next. There we go. All right, so a lot of this, we started by working with ANSTO and IRE because both institutes have a long history of working with high resolution. And by high resolution, I'm typically talking about a high-purity germanium systems. That's what I mean by high resolution. So both of these facilities have a history of doing that. And the top picture here, we have a picture of the system that is used for the at IRE that's used for the regulatory purposes. And what you have is a germanium detector that's actually the design of this particular hardware. It's looking at a flow-through cell that has a charcoal puck in it. So they're actually measuring the xenon that is slightly delayed at a room temperature charcoal puck. So they've been doing that for about 10 years at IRE. At Below, in about 2012, I think, is when ANSTO started to look at a similar thing with a slightly different design. That was a system that basically had a Marinelli-style container around a high-purity germanium detector. So both of these are two different themes along the same line that they had started to use for regulatory, or it's trying to see if they could use them for regulatory purposes. A lot of the reasons they started to look at that was they knew they were overestimating their releases by using lower resolution systems, sodium iodide typically. Just because of the lack of resolution, they were sometimes would have interferences that would make them overestimate. So they wanted to go to high resolution systems to separate out those isotopes. So basically, based on some of the experiences that both these facilities had, we started a project that was really focused on looking at looking at the backgrounds that are the xenon that's released from these facilities, because that's been mentioned, it's the largest background source in the environment. So we began to work with them and using their history, and we developed a project that's really meant to look at what is the xenon that's being released at the source term, which is what this is about. So I'll give you some example of the data. I'm out of ideas. Do I got it? So, I don't know. Next slide or something.
I think so. Maybe it's the battery.
Click it fast, click it slow. I don't know. Oh, I broke the computer. The computer froze. Awesome. No.
Do that.
All right. Well, I will, while the computer is rebooting or whatever it's doing. So this project really came out of a lot of the, radio xenon is detected in the IMS all the time. So, and it's mostly coming, or a lot of it's coming from these background sources. Yay! There's my next slide. Actually, go back one. All right. So, so we mentioned we wanted high resolution systems. So we currently have 2 systems deployed, one at IRE and one at ANSTO. Currently, they're both, the manufacturer of both these systems is Canberra, or Miriam, or whatever they're calling themselves. But we have two pictures. The pictures on the right here is the system deployed at IRE. I'll talk a little bit about how it's set up. The one picture on the left is the system at ANSTO in Australia. So I just want to point out that they are measuring 2 different points in their release. The one at IRE is the system is measuring everything that's coming right out of the stack. So very, very large gas flow through the stack, not through the detector system. The one at ANSTO is actually measuring the gas that's coming off the hot cells, which is the source of the radio xenon. But it's not mixed with ambient air from the office space and stuff. So there's 2 different points in which we're doing the measurements. The spectral formats that we're using, I'm calling it STX 1.0. It's actually very similar to basically the IMS 2.0 spectral format. It's slightly modified because some of the headers are slightly different for the for a stack monitoring system. The results is basically a modified AAR, very similar to that. We're calling it an ATS file. We're calling it a different name, so it's not mixed up with the standard IMS formats. ATS is automated time series, so that's kind of where the data that was analyzed is being stored. And then we also have state of health parameters coming out, and again, it's based on the IMS state of health formats, but it's again slightly modified for our purposes. I do want to point out, I'm not going to go into this in this presentation, exactly how all the data flow works, how we're doing how we're getting the data from the facilities to where we can look at it. I just want to give a shout out to Matthias Auer has a poster on this exact idea later on whenever the poster session is. So if you want to know more about how the data, a little bit more about some of these formats that we're trying to do, I recommend stopping by his poster later on. But this is so when you see data later on, they're both coming from these 2 systems that are currently deployed. I do want to point out we do have 2 other hardware providers that are currently building systems for us. One is a system built by NVAP, and I want to point out again, Mariana has a poster on the exact hardware and how the setup for this particular system that they're building. Again, that's in T3.1. So if you want to know more about the hardware and how it's being built and everything that goes into it, I recommend stopping by her poster later this week. So it's a very multifaceted project. So now let's jump into the data. So here's some of the data from IRE. The upper left figure is basically over a year and a half, so it goes from January 28 2015 through April 2019 of the xenon-133 over the period of time. So this detector has been operating since November of 2017 at IRE. And you see it's relatively periodic in nature with some very large releases, but most releases there's a lot of typical, what I would call releases. The other four figures are I just zoomed in to 1 week in April. This is the data from the first week of April, and that's simply because I was putting this presentation together in the second week of April, so that's why you get the first week of April's data. In the upper right-hand corner, we have xenon-133 and 135 plotted against each other. And there's a couple interesting points. There are times where you see xenon-133 being released, but not the equivalent xenon-135. And then you see a ratio, the xenon-133 to 135 ratio, changing relatively often as you go through. Also, I want to point out the very periodic nature of their releases, and that's just simply because IRE is one of the large suppliers of Tech-99 throughout the world, so they have a very routine process that they're doing to supply the world with medical isotopes. The bottom left is the same 1 week time frame for xenon-133 metastable, and then the bottom right is xenon-131 metastable. So as you can see, for the xenon-131 metastable, it's very low-level detections, and but there are times where there's high release. I do want to point out every point on here is a 15-minute interval of counting. So we're collecting data every 15 minutes for over a year and a half now at IRE. So there's a very, very large data set. But this is just, first week of April is very typical of what we see coming out of the IRE stack. So now I'm going to put this in terms of, this is just concentration releases. I'm going to put this in terms of multi-isotope plots that we typically look at in the monitoring community. There's a lot of information here, so give me a moment to go through this. So what we have on the bottom left is a 3-isotope plot, so the same isotope plot that Anders showed earlier. And on the right is a 4-isotope plot. I plotted all the data points over a year and a half that we have. So let me start on the bottom left, so the 3-isotope plot. So obviously the first thing that you notice is in terms of the discrimination line of nuclear explosions versus power reactors, you see in the 3-isotope plot, most of the data points that we see are clearly in the nuclear explosion range. So this is just showing that discrimination that's looking from a power reactor doesn't really work in the medical isotope production field. The other thing that you see, the color scheme, is the concentration of xenon-133 that was measured in each individual data point, and you see in general, as you go higher in xenon-133 concentration, you go higher in the 135 to 133 ratio. You see trends in the data that are correlating to xenon concentration. But it's not always. You also see, if you see in the bottom, right there, you see high xenon concentrations but low xenon-135 concentrations. So this correlates to the the times where you see a big xenon-133 release without the equivalent xenon-135 present. So this is kind of the 3-isotope plot. Now let me go up to the upper right-hand corner, the 4-isotope plot. There's a couple things interesting here. Is one, all the data points clearly, or most of the data points clearly fall in the nuclear power reactor domain. So we don't see very many in the nuclear explosion side. And that's a lot, and if you look at the data points, I think there's like 8 data points that are on the right side of the right side of the discrimination line. If you really go in there and you start looking at the individual spectra, you'll see the spectral fitting of the xenon-131M is not very good. So it's underestimating xenon-131. So xenon-131M. So those points are likely not real. You have to realize there's like 24,000 data points here that we have in this particular data set. So from a 4-isotope plot, it works. We clearly see the discrimination line as published as working quite well. Obviously, if you look at the colors, you see a nice gradient from low xenon concentration on the left side of the plot to the high xenon concentration on the right side of the plot. So basically what that means is as you have releases from this facility, the higher xenon 133 releases that you see, the more bomb-like the ratios are, which is unfortunate because that's the isotopes that, if we see xenon in the IMS, we're more likely to see the very large releases, which this is indicating that it's more likely to push towards out of the domain and into the nuclear explosion domain. So, but you see a clear gradient in terms of 133M to 133-1M with xenon 133. You see a nice color gradient as you go across. So this is, like I said, again, about 24,000 data points, 15-minute data points collected over from January 18 to April of 19. So this is what we see at IRE. So now we move to the next, the same thing from ANSTO. The ANSTO facility has not been, our detector there has not been online nearly as long, so I don't quite have as many points. But what I have in the upper left-hand corner is the same thing I showed as IRE. This is the xenon 131 activity over the month of April, just this last April at ANSTO in Australia. And again, you see kind of very periodic activities happening. I do want to point out that at ANSTO, they actually have two facilities currently operating. They have their old historical facility that they've typically run, and they've built a brand new isotope production facility just by the Opal reactor. Excuse me. I want to point out that our detector is on the new facility. It's not on the old facility. So this is the brand new facility that just came online relatively soon. They did their first hot commissioning run in November of last year, and they're just now pushing to full production. So anyway, this is the month of April, and again, if you go to the upper right-hand corner, you have the xenon 133, 135, and you see the same general trend. You see releases that happen without a xenon 135, but then you see a release that does have xenon 135. It just indicates you're going to have ratios that are jumping significantly across when you make a ratio out of these. Bottom left again is xenon 133M, and then 131M is of course in the bottom right. So what we're seeing here is again very periodic activity happening. I just want to point out this is the same week in April. I just pulled the same week at IRE and ANSTO. So this is what two large producers in the northern and southern hemisphere were releasing the first week of April. So again, let's take the same data. Let's move to the multi-isotope plots. And here they are again, the same plots as you saw before. Let's start in the bottom left again. Okay, good, that's left up there. This is a 3-isotope plot, and you see the same generic trends as we saw with the IRE data. Most of the data points are arriving in the nuclear explosion domain as opposed to reactor domain. We do see at ANSTO more real data points kind of trickling out into the reactor part. We did not see that with IRE. So there is a little bit more scatter in this. But again, the 3-isotope plot is, the discrimination line doesn't work with this medical isotope production. Now again, let's go to the upper right-hand corner, the 4-isotope plot. You see again something very similar to what we saw at IRE. There's a couple interesting points here is, whereas at IRE we saw 1, maybe 2 points after a year and a half of where the isotope ratios appeared across the discrimination line. Excuse me. At ANSTO, we see that happening much, much more. We see just here, there's a handful of data points that are up to or have gone across the discrimination line. So we're seeing high xenon concentrations released that are more bomb-like in nature in terms of isotopic ratios than what we see at IRE. I have a couple hypotheses as to why this is the case, but I need more data to see if we can figure out why that's the case. But again, you do see the gradient from low concentrations being far left, high concentration of xenon 133 moving to the right, And again, the high concentrations are what we're more likely to see in the IMS, and they're more likely to have ratios of higher interest. So, but you see, if you just look at the scale of the axes, these are log-log plots. So there's the xenon 135 to 133 concentration, differs by 5-6 orders of magnitude at the stack. Even and the concentration of xenon 133 will also, it varies dramatically. But just because you have a high xenon 133 concentration doesn't mean you automatically have as high xenon 135 concentration, as we saw on the previous plot. So this is just the month of April. That's what we're having. That's what the data that's shown here. So it's not so there's 96 data points per day times however many days are in April. So there's quite a few data points here. It's not the 20,000 that we have at the IRE. But we're seeing some data that's very, very, very similar in nature. So obviously the long-term process of what we should be doing with this is take this data and couple it with ATM and match it to IMS detections and look at how those are connected in time and space and ratios. Now that we have an IMS and detector systems that are better at measuring multiple isotopes as we saw earlier. So anyway, this is the data as we have right now. As time goes on, we'll get more and more data points and a better understanding of what it is. Right now, we're spending a lot of time understanding this data, going through a lot of the QA, QC processes. Because like I said, this is a computer taking the spectra, analyzing it, giving you a data point. And there's a lot of challenges in doing spectral analysis in that regime where you can have two peaks that vary, like xenon 133 can vary by 5 orders of magnitude from one spectra to the next. And how do you have a fitting regime that gives you good quality data out of that? So we're spending a lot of time right now checking the systems, making sure the state of health is working, and making sure the quality of the data is good so that we can use it further on to compare to the IMS. There's a lot that goes into that, but this is where we are right now is truly a work in progress. There's a lot of development going on, both in terms of hardware development, software development, and how do we handle this data type. So with that, we are partnering with isotope producers around the world. We are basically, they were giving this equipment for us to work with and get data out, and they've been very willing to work with us. And we're continuing to reach out, not just at these two facilities, but other facilities, to see how see how we can best integrate this into understanding the radioxenon backgrounds around the world, which is something we actually all care about. So that's what I have. I can answer questions.
Thank you, Julia. Okay, questions, Martin?
Thank you very much. Excellent talk. I'm very happy about this excellent talk. Fantastic data in the high time resolution and so many in the 4 isotope plot. That's exciting. But you mentioned already that this gradient that you observe, you have various theories and don't fully understand yet. Therefore, I don't ask you more about that. But I noticed that for the 4 isotope plot, the theoretical predictions by Paul C. and others are for a medical isotope production facility to be found with the isotopic ratio in the nuclear explosion domain. And now at the very source, at the stack, you don't find it there, the whole cluster. Do you know why?
Okay, so the question is, why does it not be where we'd calculate it to be is kind of the question. The short answer is no, I don't know. My hypothesis is xenon 131M, which is in the denominator of the x-axis. These facilities, like a particular facility like IRE, is routinely doing production every day. So my hypothesis is it's building up a burden, an inventory of 131, iodine 131, which decays to xenon 131M. So there's kind of a steady state, high level, not high level like health and safety, and it pushes all the data points to the left. And that's partially my hypothesis why ANSTO is more to the right is because they are not at steady state. They're just starting. they don't have a burden yet of iodine-131. That's a hypothesis. We'll see if the data plays out.
I had a comment there also because on the plot I showed, you actually saw the same effect from the reactor also. So it could be the same effect playing in also there, actually. It moves to the left because of 131M.
And in the 3 isotope, you don't see this because you don't have 131M.
The 3 isotope plot does not have xenon 131M in it, which is why it moves to the, not moves to the right, but it is in the right. So.
More questions, comments? If not, thanks again
Thank you.
to Dan. We are on time again. So, it's time for the last talk of this session today. And it's Martin Kalinowski talking about search for radio-xenon signals at IMS stations, possibly associated with announced DPRK nuclear tests. Please, Martin.
Thank you. Thank you very much, Anders, and good afternoon. I would like to honor the co-authors of this presentation. We are working in a team at the ITC with Pierre Bourgeois, Hakim Gedou, Jolanta Kuzmirczyk-Michulik, sitting here also on the podium, and Boshu Lu. And this is a scientific review paper. It's not a presentation. It's not much original research that we did ourselves, but I think it's a very interesting overview of the history and experience we and the whole scientific community has made with IMIS data and observations, radionuclide observations following DPRK announced tests. And of course, I want to highlight at the beginning that the monitoring system fully functions and does its purpose, fulfills its purpose with simply and only seismoacoustic detection. Radionuclide detections are not needed, but they augment, they provide additional confirmation and information if they are observed. For an underground nuclear explosion, for an atmospheric nuclear explosion, they would also, of course, always be observed. So this is the purpose of the system, to detect releases of radioactivity from nuclear explosions, and then with atmospheric transport modeling, try to associate the detection at an IMS location with a source that may be co-located in time and space with a nuclear event of relevance that could have been the fission source of the detected radionuclides. This was put to a test with the 6 announced nuclear tests of the DPRK, and this presentation summarizes what was found and reported after the DPRK announced tests. And I limit this presentation to peer-reviewed publications. And there are 11 papers that we found and that we look into here with the following questions. Which are the features of IMS observations that were used by the authors? Are there possible releases of DPRK tests that are recorded in IMS data but have not yet been detected? Of course, I can't answer this question, but I look into the theoretical possibility and what would be needed to also address this and make full use of all the IMS capabilities. So 2 of the announced DPRK tests were immediately or very short after associated with radionuclide detections. I mean, immediately after they were monitored, detected at the IMS system, but with a delay after the test. So the first one, 2006, was discovered with a prompt release immediately following the explosion, but traveling for about 2 weeks through the atmosphere because it was discovered as a clearly visible episode of level C, how we call it, anomalous high concentrations of radioxenon-133, just one isotope. And other prominent sources were excluded at that time. 2013, there was no detection following early as a detection of a prompt release, but there was a delayed release that was detected about 50 few days after the explosion, and isotopic ratio analysis made it possible to to get a timing for the fission event that is consistent with the isotopes observed, and that timing matched very well and matches very well with the time of the seismic event of that explosion. So in this table I summarize these two tests that were in one case detected with a prompt release, in the other case detected with delayed release. In the first case at one IMS station, the system was not fully built up at that time. The second case was detected at two different locations. Some authors claim they found additional IMS signals that are associated, according to their study, with the same two events. So not an additional event, but the same event, in fact, had more signatures left in IMS detections. And I just list them here for your information. But the most interesting, I think, is that the second test that was listed here, 12 February 2013, not only was detected with a delayed release, but obviously or apparently to this one paper that studies certain data at the Rittersaal facility, could also have caused the elevated levels of concentrations from an immediate, a prompt release. What about the other four tests? In fact, there were further studies done according to which two other tests imprinted signatures from radionuclide releases on the IMS system. The test on 6 January 2016 and 3rd September 2017, according to two papers, have also been recorded with some likelihood with IMS data. In one case, three stations were used, in the other case, only one. This leaves only two tests that so far no studies have claimed to see and associate any IMS radionuclide station detection to the announced nuclear tests. Now, what kind of observations were made use of? For the immediate detections that were not done in scientific studies that came out a year or three or how many years later, the immediate signatures that led to the conclusion that the test caused a signature in the IMS system are the level C concentrations, so anomalous high concentrations of one or two isotopes. And in one case also, in no case the isotope ratio flag that the IDC reports uses was indicating a possible nuclear test, but this is because the flag is tuned to only detect very prompt releases shortly after the release, not 2 weeks later. How effective are these best indicators, the most obvious indicators, in other studies for the two cases where other papers claimed that two other tests have been observed in IMS stations? So the anomalous concentration was not highly prominent in these studies. In one paper, only 11 out of 132 samples that were included in the study were level C, and actually a lot of these 132 samples were not even detections, but non-detections. We call them level A. And the second isotope, 131M, and isotopic ratios were not even considered. So instead, these papers use other indicators. What indicators are used for further technical analysis methods? For the immediate detections, the anomaly was used in 1 out of 2 cases, and for the isotopic ratios, the anomaly and the isotopic ratios was used only in 1 of the 2 cases, because in the first case there was only 1 isotope. And in addition, what the experts used were source-receptor relationships. So they looked into forward simulation consistency from the test site to the station. Possible source region was also consistent, and they also checked alternative sources that could explain the same detections. The studies that found later hypothetical detections did not consider isotopic ratios. They used the same source-receptor relationships like forward and backward modeling of the plume. They also used enhanced version of the possible source region with ensemble modeling. They used alternative source areas and the knowledge of civil sources. And they used variable emission profiles, identifying most likely emission time with a cost function. And for this purpose, they used a whole time series of about 50 samples in a row. This table summarizes all 6 tests. So you have the dates of the tests on the left side. You have the IMS stations that saw some signals. You'd see which kind of signals these are, then some indicators, and basically what we should look at, conclusion and the confidence of this conclusion. So for the 2006 test and the 2013, there was a clear association. For the 2016 study, there's only a possible association, and the confidence in this is high. And for the 3 September 2017, the conclusion is possible association, but not conclusive. So medium confidence. In fact, I can tell you that there are more cases like that. This is the typical situation that the analysts are looking for, typically for level C episodes following an announced test, and then they check whether this level C episode could have been caused from a DPRK release. Since most of the time the air is blowing from the test site across directly towards the Takasaki station, in most cases this hypothesis holds, but then it can be further enhanced, the confidence can be further enhanced by checking whether the same signal can also be explained with other known sources. And in many cases, there was a consistency with the assumption that source came from the DPRK test site, but it could also have come from other sources, therefore it was not conclusive. Now I show you the time series of Takasaki Station, Japan, JPX38, over 2 years, 2016 and 2017. This period includes 3 of the announced DPRK tests, now marked here in the timeline, and I also mark here the 50 samples that the Demeter study used shortly after the 6th January 2016 test. If you look at the time series, then you can see that even after the other tests, there were detections. Level B typically after the 9th September 2016 test, and very late the first level C. And after the 3rd September 2017 test, a lot of level B and even high level B detections and several level C episodes or single cases. So if the analysts focus initially only on level C episodes and maybe in addition on some higher level B episodes that are not as high as level C, but still outstanding and having a clear episode character, if the focus would only be on that, I'm sure we are missing a lot of information that is contained in the samples. Just consider the distribution of concentrations. Here you see the distribution chart over the concentrations at Takasaki. In green dark, you see the level A non-detections, and this is about 40% of all samples. Then level B, more than 50% in this dark yellow color, and the red samples and are level C with high concentrations. Only 3% of the samples are high concentration. But what about the 56% of samples that may contain traces of a nuclear test release, a late or early nuclear test release, but were not or not easily identified? The point I want to make as a conclusion of this presentation is that there is definitely much more information in these data than we have harvested so far, and only some studies went into the effort of going into an assessment and analysis of not just a few episodes of level C or higher concentrations or special isotopic ratios, but looking into, in this case, 50 samples over assuming a week, several weeks of delay. Three stations were used, and then eventually a possible source region was fairly limited in geographic location, so that there's a possible association with high confidence with the source of DPRK test as the cause of these detections in the whole episode to be fully consistent, like best estimate. Conclusions. The message of this presentation is we need further research and development for radionuclide monitoring of nuclear tests. The experience of the announced DPRK tests they were announced, so the whole community was alerted. Look carefully at the data. You know that we have in 4% of all more than 20,000 samples we have every day, we have a level C. So it's 1 to 2 every day. But can we afford to look into all these data every day? Typically, people are alerted by something like an announced test, and then they look closer. So how can we also make sure that test signatures are revealed even without prior knowledge of a nuclear explosion? And since most initial studies focused on mainly the anomalous concentration indicators, we need to understand how can relevant samples be flagged as of interest, possible interest, beyond the standard anomalies and indicators that we currently use. Further question is, how can we make full use of all the information that is contained in the level B observations? And I just want to highlight that the whole system sensitivity was designed to achieve a certain probability of detecting a nuclear explosion released from an underground nuclear test under certain conditions, 14 days of transport through the atmosphere, things like that. And since the systems are designed for that, the sensitivity that we measure with level B is sufficient. But if we only look at level C, concentrations, we don't at each station reach the minimum requirement of the 1 millibecquerel per cubic meter that the ops manual of the IMS requires. So next question is, how do we integrate all data that we have available? It's a huge amount of data that we have available into automatic processing, because after these announced tests, there was a lot of ad hoc analyst interactive review, but this should be automated. So not only the concentrations at multiple stations should be used, but source receptor sensitivities and known source information like Stax release data and so on should all be included in an automatic processing. But that's only the first step. Then further in-depth studies, expert technical analysis, and scientific studies should also be done. And the question for research is, which are the proper methods to be applied? We learned from studies that were published years after the event, and we need to make it available for analysts in the days after an event to be applied. So thank you very much for your attention.
Thank you, Martin. So we have time for 1 or 2 questions. Yes, Petra.
What about 2010?
Yeah, the question is, what about the 2010 hypothetical detection of a nuclear explosion? Well, I was talking only about the announced DPRK tests. And if you look in the literature, and I only refer to scientific peer-reviewed papers, then this is debated. There are some hypotheses that on scenarios how this could possibly be caused. There were detections that could possibly be caused by a nuclear explosion, but there was no seismic event found that would match this hypothesis. So I take it that it may be an open question, but in my current assessment, there was no test. There was no nuclear explosion.
Okay, thank you. So, thanks again, Martin. And thanks to all the speakers of this session. Please remain.
Wait, please.
This is not the end. We will have a poster preview, but before that, I would like to make a few announcements. You will have a possibility of voting using mobile apps. First voting is for the best poster presentation. You may go to the area where the posters are displayed and using your QR code vote up to 5 posters that you think are the best. This voting is already active, so you can start. The next voting is for the best oral presentation. Today at 6:30 till 8 o'clock in the evening, there will be a possibility of voting for the best oral presentation using your mobile app. For the presentation that you heard today, and please use this option. And the third voting is for the best poster preview. So the poster preview will be active soon. You can start voting. And now it's time for our actual poster preview. So I will just announce numbers. Those are the presentation which are uploaded in our system. And please come closer and you will be lined up and you will have a chance of your 1 minute preview. So poster number 11, 13, 14, 20, 22, 23, 25, 26, 27, 28, 29, 36, 37, 39, 40, 41, 46, 52, 56, and 57. In total, we have 20 posters preview uploaded, and that's it. I will have also poster previews.
No, I understand that. For instance, level 6 is not so powerful. Level 5 is so if they look at the data and say that's actually so should have been more than one aspect. How do we set the detection? You only want it. No, I'm talking about every day. Just the number. It's below. Yeah.
Excuse me. I'm announcing the numbers again in the right sequence. 11, 13, 14, 20, 22, 23, 25, 26, 27, 28, 29, 36, 37, 39, 40, 41, 46, 52, 56, and 57. Thank you. Each poster has 60 seconds, and after 50 seconds, a sign will be held up with 10 seconds on it, the remaining time. That's number 13, please.
Yeah, but 11 isn't here, so the next one will be 13. This poster is about atmospheric transport modeling, which we performed at the German NDC in the aftermath of the 2017 DPRK test. As you all know, there were no IMS detection of an immediate release. Then mid of September, there were some detections reported of national measurements from South Korea, which were in the media attributed to the test, but our backward simulation shows that it was rather from the Yongbyon area, not from the nuclear test site. And later on, there were those Xenon 133 detection at Usurisk, which Martin also cited in the talk before, which are now here not running at the right side. But if you come to the poster and have a look, you will see that it's meteorologically consistent with small releases, a small delayed leakage from the test site. And as we hope that this was the last DPRK test at all, there's also a summary table for radionuclide findings after DPRK tests on the poster to close this up. Thank you.
Okay, this poster explores the effect of spatial resolution of the meteorological data used to drive atmospheric dispersion models. As most of you know, some of the IMS stations are located in areas of complex terrain, and in complex terrain, meteorology can be very variable. Global analyses that are used to drive these models for dispersion may not adequately represent the meteorology in these regions. So what we wanted to do is perform a sensitivity study looking at the effects of spatial resolution on some tracers that were observed in the IMS station in Japan, and the results are shown here. We go into more detail in the poster, and we also talk about some interesting meteorological measurements that would be useful to do at IMS stations to help better understand these local processes that could have an impact on the transport and where these sources may be coming from.
Yeah, hello, good afternoon. This poster will be of interest to you if you want to work with meteorological data from ECMWF, especially in combination with the FlexPart transport and dispersion model. There is a number of different data sets reanalysis data sets, operational data sets that SMWF has produced, and they are accessible under different conditions, on one hand for member state users and on the other hand for everybody else. And there is a tool called Flex Extract that helps you to get these data in the format needed for FlexPart. And I should also mention this tool was produced on behalf of the PDS, and it is, however, free for everybody to use. Thank you.
This poster about source estimation by using combined ensemble Bayesian approach. The main advance in this methods to deal with uncertainty in meteorological fields. In this, for example, in this meteorological simulation, we have 23 ensemble simulation for the same atmospheric conditions, and we use a combined method by using ensemble approach and Bayesian approach, and the final result will be source estimation in the form of probability density functions. It may take looks like this in spatial distribution. In this poster, we make 6 synthetic sources, assumed sources, and we succeed to find 5 from 6 with good accuracy, and the uncertainty was determined. Thank you.
Good afternoon. If you would like to see our posters and you are interested how much of xenon can be detected by a remote IMS station, then please come to see our poster. You will be surprised.
Good afternoon. This poster describes measurements that were made on irradiated rocks and powders. And we looked at the fraction of both argon-37 and argon-39 that were produced by that neutron activation, and we wanted to see how much was released as measurable gas. So these are needed for accurate source term calculations, particularly in the underground nuclear explosion regime. So a brief description, the rock samples were sealed and irradiated, and once they were irradiated, they were shipped back to the lab, where they were broken open and the released gas was measured. And we looked at 5 different rock types that are listed here, both some carbonate type rocks and more igneous rocks, and then looked at 2 powders with the more specific calcium and potassium carbonates. Thanks.
Radioiodine, and specifically 131, is not one of the most interesting radioisotopes for nuclear explosion monitoring if we see it alone. Actually, it's seen in 1 per mil of all samples. In 200,000 samples, we saw it almost 3,000 times already. So what do we learn from this? A lot of these detections followed the Fukushima event, so there is a lot we can learn, or the community learns from this. But also, radioiodine 131 is a precursor of xenon-131N, and therefore very important to understand its sources if we want to understand the radioxenon detections. Thank you. I want to mention together with Hakim. I have another one. Now, right now, sorry. I'm back again, sorry. Radioxenon. So we established a source inventory of radioxenon for the calendar year 2014. It was now updated with best information from reported sources, from a lot of nuclear power plants and from medical isotope production facilities. So this data set has been updated. It's now being used in further studies. You will hear about another poster from Hakim Gedou in a moment, where we use these data. And this poster was done together with Halit Tatlitsu. Thank you very much.
Makiko, Furuno of JAEA. The purpose of our study is hemispheric dispersion analysis to verify the latest source term for the Fukushima Daiichi nuclear power plant accident, estimated by JAEA, and to estimate contribution rates of each release date to simulated concentration. The scatter diagram shows that daily cesium-137 concentration shows that our simulation generally agreed with the observation from CTBT IMS data. The light figure shows the time series of daily cesium-137 concentration of one of the overestimated point Hawaii. We analyzed that this overestimated estimation is mainly caused by cesium-137 release from 70 to 19 March 2011. This information will help to improve the estimated source term. Thank you.
Good afternoon. This poster is discussing the STAX data that Judah Fries mentioned. It's how we took a year's worth of data at the UK's NDC and developed tools to allow us to process this. We put this in context of detections in Sweden, SCX-63, and a hypothetical nuclear test to prove how STAX data would be used by an NDC to disprove a nuclear test and say it's come from a medical isotope production facility. Thank you.
I hope you didn't miss the excellent oral presentation by Puni Tayebi earlier in this session about the radioxenon emissions from nuclear research reactors. And as a byproduct of this study, we worked together to make an assessment of argon-37 coming out of research reactors. And it is not a small source or likelihood to be released, because whenever air gets irradiated, ambient air gets irradiated by neutrons, then argon-37 is produced. This is more likely for a research reactor to be released than from a nuclear power plant. So it's interesting to have an estimate of the global source of all the more than 200 nuclear research reactors for this isotope. Thank you.
So good afternoon. In this poster, we present a study where we investigated specific historical radioxenon background detections in the international monitoring system. So we looked, in fact, at observations for the full IMS, and we selected a few specific case studies. And here we selected detection at CAX-17 and GBX-666, where we, in the Belgian Nuclear Research Center, we didn't quite well understand the detection at GBX-666, At the Canadian one, of course, we know it's influenced by a medical isotope production facility. And so we wanted to compare different use of source receptor sensitivity fields to see how it could help us to understand detections we don't understand for the moment. So if you want to see the poster, it's 2.4p37. Thank you.
Hi. Melt in a nuclear cavity is likely to control part of the radionuclide inventory release to the atmosphere. As illustrated here in the left for the Rainier underground nuclear explosion, nuclear cavity is a complex mixture of melt and rubble fallen from the chimney above. If you want to learn more on what happens when a block of granite or other rocks falls in a melt puddle, please come to our poster. And as you can see, this is a collaborative project between CEA France, Livermore Laboratory in the US, and the University of Paris. Thank you.
Hello, my poster is about, with my colleagues and of course, is about subsoil sampling of gas. We have collected almost 50 samples at 10 different sites and looking for argon and xenon as a study of the natural background. And we were able to detect both radioisotopes at in several samples and at several sites. So please come and have a look at the results. Thank you.
The poster is about the 214 baseline for radioxenon. There was already a publication on this in 2017, and the work done here is to update both the observations, results, but also the simulation, the simulated impact from known sources. So the poster number is P46.
Good afternoon. The main goal of this study has been to perform a detailed statistical analysis of the atmospheric background and of the radioxenon anomalous concentrations measured at some IMS stations. After making a descriptive analysis, two different types of control charts were being applied at the overall chronology of the observations. The Shuar chart sensitive to large variation and the IVMA chart sensitive to small variation. These two charts were being applied in order to identify and study those values that significantly deviate from the average value of the radioxenon concentrations. The control charts method were being finally compared with the interquartile range method currently used by the IDC. But the use of the control chart method like a complement of the IDC method could be further investigated. Thank you.
So this is now about the 8 years of reviewed noble gas data from the 25 certified IMS stations. And it provides an overall picture in terms of detections, categorization, distribution at different sites, but also in terms of range of detected activity concentrations. It also shows a clear correlation between the site location and the medical isotope production facilities, but also nuclear power plants for some stations. So the poster number, as it is already here, is 56.
Hello everyone, I think this is the last poster. This is an update of an IDC project on high-resolution atmospheric transport modeling, where we explore the possible applications and do a validation of the high-resolution atmospheric transport model. We use 7 episodes of elevated radioxenon detections in Freiburg in Germany and do atmospheric backward simulations to match it with release data from Belgium and then make a statistical comparison of different output resolutions and validate it against the operational FlexPod model that is run at the IDC. Thanks.
Thank you very much. I would like to let you know that tomorrow at 5:15 we will have a second part of poster preview. So if for some reasons your poster is not uploaded here, then you have the second chance, and we can use this time to do the second round of poster preview. Please vote for the best poster preview. Please check also posters. We would like to ask authors of posters to be present tomorrow at 4:30. So then we all could have a chance to talk to authors of the posters. So with this, I would like to conclude the session of today and invite you tomorrow. Thank you. In front. Yes, 5:44. Okay, thank you. It is in the program. It's 5:15. Info. Yes, it is posted. Yes, it is 2.4. It's, you see. So we can do this.
Hi, may I ask? I'm not one of the missing and who do I talk about getting
You may ask us for the conference.
Thank you.
Yeah, we can just go for a coffee. I think there is another provider John is
Change orders.
Yeah, we can just talk.
You have no problem.